Hi folks, this year marks the 25th anniversary of the launch of the Hubble Space Telescope, and to mark the occasion, NASA is taking and releasing new pictures of old favorites, such as this picture of the Eagle Nebula and the famous Pillars of Creation. I'm going to take some time to go into some recent Hubble history and look at a photo that went around on YouTube just back in 2013, and a lot of people were talking about it, and we're going to discuss it, and I'm going to give you guys a new tool that you can use should this sort of event ever happen again, that you can use to check and see what's going on. So back in 2013 we had Comet ISON, and Hubble took a couple different shots of ISON, and in one of them it was tracking on the stars and taking long exposures of the comet as it moved through space. It tracked on the stars so that it could reveal the stars and galaxies very sharply and overlay one of the pictures of the comet back onto that stack. Now, the raw stacked images were also released online as with all other Hubble data, and some people pulled it up and noticed it looked really strange. Now, initially, what they saw was this. They went on to one of the Hubble Legacy Archives websites and pulled up a preview image of the raw FITS file. Now, that preview image is not intended to represent everything that's in the data. These images are high bit depth FITS files. And as I've mentioned before in previous videos, such files require special handling techniques. You need special software to handle high bit depth FITS files because your monitor and your computer normally display 8-bit images. They can't display the full dynamic range of, say, a 32-bit image like you get from Hubble. But the preview window is only designed to show a particular portion of the histogram at a time. You can make the image darker or lighter and look at different portions of the histogram, but you can't see it all at once because your monitor can't display it. Your monitor is incapable of displaying dynamic range that is that incredibly wide. So a lot of people didn't seem to understand this, and moreover, YouTubers who were talking about it tended not to have software for handling high bit depth FITS files, so they thought something was being covered up here. But in truth, if you pull it up in a proper program and process the images into 8-bit images properly, you do see what is being hidden there. Nothing's really being hidden there. It's all there in the data. You just have to know how to handle it. So there's what appear to be 3 objects there where ISON is. Now, people who use the FITS viewer online were also able to darken the image and look at the portion that was blown out before. The pictures were not actually overexposed. Again, all of this information is actually there in the FITS file. It's just that when you're looking, say, at the brightest portion, like you are here, you don't see the dimmest portions of the image. They simply look black. So you can only see a portion of the histogram at a time because it's such a high bit depth FITS file. But beyond that, what people were talking about are these lines here, wondering what's going on there. Well, back then, I released a couple videos talking about it, mentioning the fact that it's actually parallax. And I pulled it up in Celestia and showed what Hubble should see from its perspective in orbit. But a lot of people weren't satisfied with that. Some people asked to see the math. They want to see mathematical proof that that's what should be going on, because it just doesn't make any sense to them. I don't know what people were really thinking, whether they were thinking that there was something that Celestia was doing to try to cover this up or make it look normal. I don't know. But in any case, to cover this subject again and highlight a popular favorite from recent Hubble history, I've created a new spreadsheet that calculates the apparent position of a comet as seen from Hubble as it orbits the Earth. So, as I said, a lot of channels talked about this image, but no one really looked at what Hubble should have seen. That should always be the first thing you do, say, okay, something looks strange, well, what should it look like? Maybe my preconceived notions of what it should look like are wrong. Well, there are various ways of exploring that, but really you don't have to take anyone's word for it, even mine. You can do the math yourself. That's what I've done here. I've just done the math on this image and found out what it should look like according to the orbital elements of the comet, Earth, and Hubble. So that's what this spreadsheet has. We have the orbital elements of Comet ISON, and it calculates the ecliptic longitude and distance from the Sun of the comet. If you scroll down, here's the orbital elements for Earth. and it calculates again the heliocentric ecliptical longitude and distance from the Sun of Earth. And then if you scroll down some more, we have Hubble. Now, we have Hubble's orbital elements, and again, this is pretty much calculated exactly the same way as with Earth, only of course Hubble is orbiting Earth, so the orbital period is much shorter. It's about 95 minutes. And there's also one other catch. You have to keep in mind that Hubble's orbit is inclined 28 degrees to the equator. When they launched Hubble 25 years ago, it was launched due east from Florida. And from Cape Canaveral, if you launch due east, the inclination you're going to end up at is about 28 degrees. Now, they launched due east to maximize the advantage you get from launching with the Earth's rotation, to get Hubble up as high as possible, because it doesn't really have any thrusters to reboost its own orbit. So they took the shuttle as high as they could possibly get it with Hubble on board and put it at that altitude to maximize its lifespan. And in fact, when they would go up and service it over its lifetime, they would occasionally reboost it as well, because Hubble has no way of reboosting itself. So on the final servicing mission, they attached a sort of docking module to the back of the telescope, so that eventually, when the orbit gets real low and it's getting ready to re-enter, they can send up an unmanned vehicle to attach to it and bring it down in a controlled fashion so that it doesn't land on anyone's head. So you have to keep that in mind, because when you calculate the orbit of Earth, there is no inclination. Earth is on the ecliptic by definition. Hubble does have inclination, so you have to bring that into consideration. In particular, when you calculate the true longitude is actually made up of three components. The longitude of the ascending node, the argument of perihelion, and the true anomaly. Now, the true anomaly and the argument of perihelion, perigee, I keep saying perihelion, perigee in this case, Earth is the point of reference here, those two are out of plane. They are in the plane of the orbit, which is 28 degrees inclined. So you have to rotate those back into the plane of the equator to find out what the actual geocentric longitude is, which is more in tune with what you might be familiar with when you think of longitude on the surface of the Earth. So the spreadsheet does that. It also compensates for the oblateness of Earth in calculating the geodetic latitude. And so what you have here is you have the position of Hubble at a given point in time over the Earth, the latitude and the longitude, the altitude. So you can use this as a sort of virtual observer. You can treat it basically as a fixed point, as a fixed observer, as if it were an observer on a mountain 558 kilometers high. Of course, Hubble isn't just stationary, it is moving. But for each new point in time that you specify, the information changes. It moves with Hubble's orbit. So what you have here is the ability to calculate where the comet should be seen from the position of Hubble as it orbits the Earth, and that's exactly what this spreadsheet does. The key to that is, of course, calculating the parallax. Yep, I said it. It's parallax. So you have to take into consideration parallax, and in this case, the maximum amount of parallax you're going to get as Hubble orbits the Earth from one side to the other. At the distance of the comet, an object will have a maximum parallax of about 2.2 arc seconds. Here it is in degrees. As you can see, it's a very small angle. But Hubble has a lot of angular resolution. It sees down well below arc second resolution. So 2 arc seconds to Hubble is actually quite a lot. And so you have to take that into consideration. And you do that with a series of formulas that I pulled from a book published in 1863. The formulas I used here are listed as 134 to calculate gamma, and then use that in one of the other equations, equation 138 and equation 140, and those are incorporated in the spreadsheet. So the spreadsheet calculates the position of the comet as seen from Hubble, taking into account parallax, basically using the same formulas you use for an observer on the surface of Earth somewhere. But of course, Hubble is off the surface. But it takes that into account. It uses the altitude of Hubble in this case, about 558 kilometers at that time. So from that, it generates the apparent position of the comet in both hours, minutes, seconds, degrees, minutes, seconds, and in decimal degrees. So if you do this over the images that you saw here, you're seeing in these pictures, you're actually seeing a stack of 3 separate images, not just one image. So I can actually pull those up, and you'll see it here. So here's one image, here's a second image, here's a third image. Those were all stacked, and when you stack all those images together, this is what you get. So you get this image here. Now some people said that this can't possibly be parallax because the comet's tail, it's pointing in a single direction. Well, we'll cover that in a second, but basically the comet's tail is pointing in a single direction because what you're dealing with here is a translation of the apparent position of the comet, not a rotation of the image. So the tail will point in a consistent direction, but we'll see that more in a second. First of all, I would like to show you guys what happens when you chart out what should have been seen over the imaging times that were taken. So you can actually find out the exact time each of those images, each of those three pictures were taken. As you can see, it was taken on April 30th, 2013. And I've got the exact times, and I've calculated the apparent position of the comet as seen from Hubble at those times, at the start, the midpoint, and the end point of each image. So there were three images from the pictures that you saw there. And here's the start, the midpoint, and the end of each image and the corresponding coordinates of the comet in decimal degrees. Now, if you graph this out, you can actually recreate the image. You can mathematically predict what the image should look like, and that's what it should look like. There it is, the infamous three-object comet ISON. So what we have here now are a series of coordinates that are predicted for ISON as seen from Hubble. Now again, Hubble was tracking on the stars. That's why the comet is moving, because the comet is moving relative to the stars. The equatorial coordinates, the grid here is effectively the same as the stars. It's fixed, and that's what Hubble was tracking. The comet is moving relative to that over time, and over the course of those three images, it forms this arc. So we can basically simulate that image now with a real image of a comet. So I took this picture of comet C2012 K1 Pan-STARRS last year, and you could see it's not perfect for this purpose because the nucleus is a little bit streaked here. I was tracking on the stars, much like Hubble, but of course my telescope was not orbiting Earth, and so the comet just forms a straight line because there's no parallax there from me orbiting the Earth because I'm not orbiting the Earth. So ideally, for this purpose, it would be a single point instead of a line, but we'll use it anyway. Basically, what we're going to do here is take 9 copies of this image, simulating and basically recreating the start, midpoint, and endpoint of each of Hubble's images as it was tracking the stars and as that comet was streaking. We're going to use the offsets, the difference between each of these sets of coordinates as offsets to stack our own image. Okay, so for instance, the end point of this image was offset, the comet was offset from the beginning point at a relative distance of 5 pixels in the x-axis and -1 pixel in the y-axis. Now that's -1 in terms of GIMP. I actually inverted the y-axis here from what you might expect because GIMP regards the top left corner of the image as the origin, not the bottom left. So basically what I've done here is I've just taken the difference between each set of coordinates and multiplied it by a factor of 10,000 because this is in, again, this is in decimal degrees here and we're talking about very small angles. So to simulate this as an image, stacking an image, I've multiplied it all by a factor of 10,000. And that gives us these nice little integers we're going to use to align the images and simulate Hubble's image. And when you do that, here's what you get. There it is. You can see the main thing here to look at is the fact that, again, the tail is pointing in a single direction. Some people were pointing this out as evidence that it was not parallax. Well, actually, that is what you expect with parallax because it's a translation of the comet's position over time as the telescope is tracking on the stars and doing long exposures of the comet. And what you get from simulating it is the same thing that you see in the actual Hubble image. So indeed, that is what we would expect. So next time, if there's another major comet that catches the public's attention and they take a picture of it with Hubble, and you see something strange going on with it, especially if they're tracking on the stars and you see the comet streaking in some strange direction, or even if the opposite is true and they're tracking on the comet, you see the stars streaking in some strange direction in the raw images, you can find out whether or not it is as expected by using the spreadsheet. The only thing you have to do is update the orbital elements of the comet, which are here. If you want to do that, the numbers that need to be updated are the ones that are in bold and italicized, and then update the elements for Hubble, because Hubble's orbit, as I mentioned before, is slowly decaying, and it's slowly coming back towards the atmosphere. So you need to put in contemporary elements in here. These elements are actually from 2013, from when that image was taken. So with that, I'll just say clear skies, and thank you for watching.